Welcome to the PTCS heat pump sizing class. Heat pump sizing in the PTCS program is critical to the energy savings and also to increasing year-round comfort for your customers. The benefits of the HVAC design process should be clear. Yes, we do want energy efficiency, and that's what PTCS is primarily about. But if we do size the equipment right and design the whole system, including the duct system correctly, we get greater comfort. We'll get less cycling on the equipment, which makes it easier on the compressor. We'll get lower auxiliary heat use, which is primarily where the energy savings from PTCS come from. And if we do everything right and make everybody comfortable and their bills go down, we'll get more customer compliments and fewer customer complaints. I know there's lots of rules of thumb out there. 1 ton per 400 square feet has been around for a long time. If that was ever correct, it was probably for a largely uninsulated house with single pane windows. So if it was ever correct, it's probably not correct today in modern homes with insulation and higher degree of air tightness. The 1 CFM per square foot of house, I know that's out there. Tonnage, this is my favorite, half the number of cylinders in the customer's biggest car or truck. What's in the shop today, and of course, keeping up with the Joneses, half-ton bigger than the neighbors. And of course, we have other ones such as this nice little cutout over here where you stand across the street on the curb and see how big the house takes up. The heat loss, heat gain analysis, the math is really pretty simple on it, and it's part of the ACA process. Manual J, which stands for Joule, is the heat loss and heat gain calculation. Manual S is once you get that heat gain and heat loss calculation completed, what's the best piece of equipment to put in that house. And Manual D stands for duct design. If you've never taken a duct design class, I urge you to do so. Getting the airflow right is critical to efficiency and capacity. So what are the penalties if you don't do things right? So if you're going to size right, you absolutely have to install right. And one of the biggest problems in heat pumps, as we all know, and air conditioners, is low airflow. This chart right here, if we start over here at 0 deviation from full airflow, basically we're saying we're getting 100% of the capacity. As we get down, say 20% low, we only have 90% of the capacity and 90% of the efficiency. And as we go down, we see that both the capacity and efficiency decreases as the airflow decreases. If you sold somebody, say, a 14 SEER air conditioner or a 10 HPF heat pump, if you do not have the correct airflow, they're not going to hit that goal. So once again, to size right, you have to install right. I know you probably all have the Hall of Shame photos from your competitors' shops that they installed. Manual J heating loads, it's really pretty simple on the heating side. It's that old Greek formula, if you will. It's UA delta T, or the U value, times the area of the basics of the building's components times the delta T. So basically what you do is you get the square footage, you look at the YAR and the U values. You get a duct multiplier, and duct multipliers, even if you do a duct leak test, is an estimate. If you don't do one, it's an educated guess. Air changes per hour, homes have certainly got a lot tighter. And when you're doing that, for any kind of furnace, you end up with, 4 or 5 basic choices. Manual J cooling loads, they get a little more complicated. One, again, you need the square footage and the U values. On windows, orientation is critical, shading, solar heat gain coefficient. The modern window lets so much less solar radiation through than it did, say, even 15 years ago. Duct multipliers, again, all of you on the webinar today have probably been in hot attics, and we put ducts up there, and the ductwork might have 65-degree air in it, and the ductwork might be in an environment where the attic's 135 degrees. That's a pretty big delta T. So yes, you're going to hear us, talk about the importance of at least looking at the duct system today. The internal gains, that's all the humans and the stuff that they plug into the wall and the narrow range. And you notice we have a lot more choices when it comes to heat pumps. They come in half-ton increments, which makes the need for precision a little higher. A word about duct multipliers. Yeah, this is kind of a funny picture. It's obviously a test house with a return running outside. But if you think about it, that's probably a more hospitable environment than the attic on this hot day, having it in the front yard. Typically, it's between 5 and 10%, and the duct multiplier is the penalty anytime you put the ductwork outside the house, either in the attic or the crawl space, sometimes the garage. 10% is about as good as you can get. That's well insulated and that's almost airtight. 20% sort of normal. And if it's 30% or higher, you really should consider fixing the duct system. It's hard to make people comfortable with a bad duct system that delivers warmer air than expected in the summer and cooler air than expected in the winter. So we hear a lot, so why can't we just sort of size by square foot? And really, more than square footage, it's the R value that matters. Over here, we can say basically this is the square feet of attic at various R values needed to create 1 ton of heating load. That's 12,000 BTUs per hour in Boise, Idaho. Boy, if you had an R0 attic, it would only take 500 square feet to create that 12,000 BTUs or 1 ton of load. By the time you get to R19, a big difference, you'd need 4,000. But at today's homes, with almost, a lot of homes out there having an R38 or higher, it takes 7,500 square feet. So what's more important than the size of the house is the R value, the U value, the heat loss, heat gain. This is another way of looking at the same information, if you will. This is BTUs through a 2,000 square foot attic with various R values. Again, we're in Boise again. At R0, oh my gosh, 42,000. That's a gas furnace all by itself. By the time we get down to R7, we get a big jump down, and R38, boy, we're much lower. This is not to say that high R values aren't important. Why not stop at R11? This is to say when it comes to sizing of equipment, the biggest differences come when you make a low R value higher. Let's get some definitions out of the way. Design temperature is not the coldest day of the year or the hottest day of the year. Usually the coldest day of the year happens at 2 or 3 in the morning. Chances are the house has enough thermal mass, if you will, it's already heated up, that it can ride through those few cold hours. If we size equipment for the hottest or coldest day of the year, we would probably have 2 systems in every house, and everything would cycle and lots of comfort complaints. Winter design condition, it means it only gets colder than 1 or 2.5% of the time, depending on what number you tend to use. In Boise, the average coldest temperature is -2. This is also called the mean extreme. However, the winter design condition is 9. In summer, let's be honest, your customers, what do they care most about? I want it cool, and I want it cool now. Portland is sort of the opposite. Our winter design temperature is 23, and the summer design temperature is 86. This 86 degrees, well, that is a very common summertime temperature. It's typically not the reason people buy air conditioners in Portland. They want to be able to cool their house when it gets 90, 95, or even on the rare day 100. So we're going to talk about the mean extreme a little bit later on today. Definitions: heating and cooling load. The heating or cooling load of the house is how many BTUs per hour, just like how the equipment is rated. The house requires to maintain the required indoor temperature at design conditions. Typical homes have heat loss rates of between 20,000 BTUs an hour and 80,000. Cooling loads typically range between 12 and 40,000. Equipment sizing. Relax, don't panic. There's sort of this old adage in the HVAC industry that close counts in horseshoes, hand grenades, and heat loss. This is not to say go out and guess, but the difference between an R38 and an R42 or an R33, this won't make much difference. The main thing is, get close. Get close, and it works. Most of the time we get to relax. What's meant by equipment sizing? What the customer wants: to be warm in winter, to be cool in summer. Pretty simple. They called you out there for a reason. When equipment sizing is really important. Furnaces, they have to be big enough to heat the house. Modern furnaces do not have much of a penalty for oversizing. People like to heat their house up in a hurry. That's why many contractors and consumers like 2-stage pieces of furnaces. Keep it within a nick size and everything will be fine. relax a little bit. Air conditioning. We are really fortunate. We live west of the Rockies. When we get hot days, we have low relative humidity. If you ever think you're having a humid day west of the Cascades, I really recommend that you get in your car, drive to the airport, and drive to New Orleans, where you'll really realize what mugginess happens to be. Heat pumps. Heat pumps are a little more tricky to size. They have to be big enough to heat the house down to 30. That's our recommended balance point. It's time to sweat the details a little bit. Getting the right size is crucial to saving energy and making the occupants comfortable. It's probably not panic time, but the level of detail needed to size heat pump equipment is a little higher. On furnace sizing, it's really pretty simple. You calculate the heat loss at winter design conditions. Size the furnace not to exceed 140%. That's ACA's guideline. In the average new house, the heat loss is about 20,000 BTUs. The smallest furnace you can buy really is 40,000. So you're already twice oversized, and I don't hear too many complaints because of that. Obviously, we can get absurd and start putting 100K furnaces in homes with 20K worth of load, and you're going to have comfort complaints and probably some equipment problems also. And yeah, PTCS realizes that sometimes you just need to put a larger fan in the air handler to handle the air conditioner sometimes. So furnace sizing, it's really sort of easy. It's really simple. You just sort of get the capacity tables out with. This one here is for a two-stage piece of equipment. It tells you the input at 40K on high, 26K on low. The output, this is obviously a high efficiency furnace, is 38 and 25. And again, we size on the output of furnaces, not the input. So real quickly here, what would be the right size unit for a house with 36,000 BTU hours worth of heat loss? There's not a big difference in cost in furnaces, so upsizing doesn't cost the customer too much money. But if we had 36K here, we see this 45K furnace here. The output's 36, so we'd probably say, I don't know if I want to be on the edge here. I think going up one size would be perfectly acceptable. What makes difference in sizing between heat pumps and furnaces? Well, the big thing about furnaces, they maintain their output regardless of the outdoor temperature. When it's 50 degrees outside, they have the same output as when it's 0 degrees outside. Heat pumps, on the other hand, they change with the outdoor temperature. The colder it is, the smaller the capacity of the heat pump. And I do realize there's new cold climate heat pumps on the market, extended capacity heat pumps, if you will, but they still respond to the outdoor temperature in interesting ways, and we need to take a look at their detailed capacities also. So this chart just sort of reinforces what I said before, is that here we have a furnace in orange, and we can see at 47 degrees, which is the orange color, it'll give you 64,000 BTUs. And sure enough, when it's 35, it gives you 64,000 BTUs. But a 5-ton heat pump at 47 degrees would probably give you something close to a 60K. At 35, you're honestly down, to almost a 3.5-ton unit. Let's look at a 2-ton unit over here. Sure enough, at 47 degrees, it's 24K. But by the time you get to 35, really you have a 1.5-ton machine. Heat pump goal. Heat pump goal in PTCS is to maximize the savings from heat pumps. In order to do this, we need correct sizing, a control strategy that minimizes the amount of strip or auxiliary heat, and a high efficiency heat pump. Keeping the strip heat off is the key to maximizing energy savings. Say a 3-ton heat pump is drawn about 3 kW and there's 15 kW worth of backup. Boy, as soon as that 15 kW backup comes on, you go from 3 kW all the way up to 18 kW. You basically increase the energy used by a factor of 6 when that happens. This is a detailed capacity from a manufacturer. Some of you might recognize the brand. This is interesting. It's a 2.5-ton unit, and at 47 degrees, their 2.5-ton unit gives you 28,000 BTUs. Not exactly a 2.5-ton, machine, but close to it. It's like a 2x4. It's a nominal value, and we should always look at the detailed capacity table. So this is the capacity of a single stage system, if you will. Down here on the bottom axis, we have the outdoor temperature ranging from 0 all the way up to 70. The capacity over here at the capacity per ton. So basically what we can see, sure enough, at 65 degrees, wow, we're above our full rated capacity. That's good news. By the time we get down to, say, 47 degrees, we're right at about 12,000 BTUs per rated ton, exactly where we'd be. And as we go down, we hit what's called the defrost knee, if you will, because at this temperature, you can make a lot of ice, and there's generally a dip in the capacity. But in general, the colder it is, the less capacity the heat pump has. Yes, we now have some extended capacity heat pumps whose curves look very different. Notice that the peak capacity on this system is at 27 degrees. It's actually higher there than it is when it's 52 degrees. Does this make sense? Yes, we don't need full capacity from the compressor at 52 degrees. It's much more likely that we'll need the full capacity at 27 degrees. And we can see that it dives off the colder it gets. Here's another system that's an extended capacity system. It's a little flatter. This one does have higher capacity at warmer temperatures, but notice this very flat spot here, roughly between 27 and 47. That's sort of where we live in the Northwest, so your capacity remains flat through that temperature range. Keeping the strip heat up, how do we do it? We size the compressor large enough to provide heat for the house all the way down to 30 degrees. 30 degrees is a balance point we like to see. It gives you a nice mix of capacity and a nice mix of efficiency and a nice happy homeowner that isn't freezing when it gets cold outside. In order to do this, we have to size correctly. And notice that we call the lockout strip heat at 35. That gives you sort of 5 degrees of flexibility, if you will. If you size for 30 and keep the strip heat off at 35, you'll avoid unwanted customer complaints.